In this section, we'll be talking about a family of functions called hyperbolic functions. We're going to find that they are similar in the way that they look and the way that we manipulate them to typical trigonometric functions. Now, and it's probably no surprise if we know something about how the hyperbolic functions were developed. They were actually developed in the 1700s by a Swiss-German mathematician named Johann Heinrich Lambert, and a picture of Mr. Lambert is in your textbook. And actually he worked with, or he derived his formulation of hyperbolic functions from three other mathematicians, a mathematician named Cotes, de Moivre, and Euler. Now, de Moivre and Euler you may have heard of. I've seen their names from time to time in many different textbooks. Cotes I haven't heard so much about. But at any rate, the information sort of came to him from several directions, and perhaps because of that, we can think about hyperbolic functions as related to other areas of mathematics in several ways. Here's one. Now, I want to just show you the similarity between the development, sort of a backdrop for hyperbolic functions and the backdrop for trigonometric functions. You know, with trig functions, we use a lot of the development involves the unit circle. So we have this unit circle, and you know, we talk about a point x, y on the unit circle, and we can talk about triangulation with that point and all sorts of things like that. All right, so we develop all of that. But just think for a moment about the equation related to this circle and just this part of the circle. We know that the equation of a circle is x squared plus y squared is r squared, where r is the radius. Well, the radius here is 1, so this would be 1. Now, if we solve this for y squared is 1 minus x squared, so y is plus or minus the square root of 1 minus x squared. And since we're talking about only the top part of the circle here, for simplification purposes, I've just used the positive version here. So square root of 1 minus x squared. Now, the hyperbolic functions can be thought of as a derivation of a unit hyperbola. Now, unit hyperbola, that's this a hyperbola which might be situated like this on the coordinate plane. The vertex of one branch is up here at the point 0, 1. We would presumably have another branch down here, but let's just think about the upper branch. Now, we know that for hyperbolas whose center is at the origin, we have this as our form for the function. Now, notice the y appears in the first numerator, x in the second numerator, and that's because we have a vertical transverse axis. Now, because we have a unit hyperbola, a and b are both 1. So take a and b out sort of in these denominators, and we have this. And solving for y, we find y to be plus or minus actually the square root of 1 plus x squared. Since we're only talking about the upper branch, though, we have this. Now, look at the similarity between these two. You see, very, very similar, and someone developing the ideas about hyperbolic functions, about this unit hyperbola, could follow a very similar kind of logical path that would be followed with the trigonometric functions over here. Now, because of those similarities, I have so much to tell you in one moment in time, it seems like, right here, because we have identities involved, and we have to look at the functions, and we've got identities, and we have derivatives and integrals and inverse functions and all of that to talk about all at one time. Now, because there is so much, such a broad amount of information that we're going to talk about here in just this one little section, we're only going to scratch the surface about the study of hyperbolic functions. This is really just a cursory introduction to the idea. That's really all there is to it. We're going to work a few problems, and that's our main focus here, is to work problems using the different ideas that we're going to talk about. Let's look at the functions here briefly. The hyperbolic functions. Now, notice SINH. This is the hyperbolic sine of x. The hyperbolic sine of x. And it's defined as e to the x minus e to the negative x all over 2. Now, this could be rearranged, you know, as 1/2 times this numerator, and just another form algebraically, but This is what it is. Now look at the hyperbolic cosine of x. It's just the sum of these same items that we had up here as their difference in the numerator. And the other hyperbolic functions just come directly from these two in very much the trigonometric sense. That is, we use our ratios and our idea of trig relationships to generate the other hyperbolic functions. And we can see here that tangent is sine over cosine, or hyperbolic tangent is hyperbolic sine over hyperbolic cosine, and so forth. And then we have the reciprocal functions over here. All right. Before we go on with some other information, I also want to tell you that I mentioned that the development of hyperbolic functions can be thought of as emerging from a number of different areas. It turns out that in formulating differential equations, which is what integration is sort of all about, but in formulating differential equations, a lot of times e to the x or e to the negative x or combinations of those two, sums and differences, for example, emerge quite often. So it may be no surprise that hyperbolic functions appear often in the study of differential equations. So they just kind of pop up all the time because of this kind of arrangement for hyperbolic sine, hyperbolic cosine, and the other hyperbolic functions. Well, all right, let's go on and talk a little bit more about how these are useful. And by the way, the graphs of these hyperbolic functions are in your textbook. I invite you to look at them. We don't get a lot of mileage out of them here, but I think it's kind of interesting to understand that, you know, if this 2 is thought of as the denominator for both terms in this numerator, then we think of this, we think of that as separate items. And we could actually graph this, we could actually graph that, and think about the difference of those two, you see, as giving us this. You see, and in the text, you'll notice that there are some overlays on the graphs that will illustrate that quite well. Interesting kind of development and association with that e to the x, e to the negative x idea. Well, hyperbolic functions are used in these various areas. They describe the shapes of electrical power lines. They describe motions of waves in elastic solids. They describe temperature distributions in metal fins that cool hot pipes. Now, all of these seem to be rather esoteric and focused kinds of interest for hyperbolic functions, but take a look at this. Pursuit curves. Now, we'll actually work a problem involving a pursuit curve here in just a little bit. And here's perhaps the most interesting one, the geometry of the general theory of relativity. Pretty broad and high impact kind of situation involving hyperbolic functions. Well, I mentioned that many of the aspects of trig functions and hyperbolic functions are shared. That is, there are a lot of similarities like that. There are a number of identities associated with hyperbolic functions, and again, they're written in your textbook, and there's no sense in me just rewriting them here. You can look at them for yourself. But I want you to understand that we can verify identities in very much the same way that we verified identities before. That is, we can verify the identities involving hyperbolic functions just as we verified identities involving trig functions. For example, here's one of the many identities that are listed in your textbook. And if we wanted to verify this, then what we would do is go back to our definition of hyperbolic cosine, hyperbolic sine. Now, this hyperbolic cosine squared x means hyperbolic cosine x all squared. So we take the definition for hyperbolic cosine x, which is this, and then square it, and then here hyperbolic sine x squared. You see, and now just massage this algebraically, squaring in the numerator, you see, multiplying binomial times binomial, this times itself, we get this. Now, I'm emphasizing the middle term here as being e to the 0 power. After all, if we're, well, let me go through it. If we have e to the x times e to the x is e to the 2x. And then e to the negative x times e to the negative x is e to the negative 2x. And the middle term, you know, is just double this product, you see. And this product is e to the x times e to the negative x is e to an exponent which is x plus negative xg, that's 0. So that's why I have this here. So it's 2 times e to the 0 is simply 2. And in a similar way, we square this numerator over here. Squaring the denominators is relatively trivial. But then we want to subtract here. So we're subtracting really this numerator and changing all the signs. So it's minus this plus that, then minus this. And then we see that a lot of like terms go out. We have e to the 2x minus e to the 2x. They're out of here. Then 2 plus 2 gives the 4, and e to the negative 2x minus e to the negative 2x, they go out as well. So we have 4 over 4, or 1, so we verified this particular identity. So we go through that process in much the same way that we do with the trig identities. Here's a list of derivatives of hyperbolic functions. It starts out rather simply. The derivative of hyperbolic sine of some expression you see involving x presumably would be the hyperbolic cosine of that expression times the derivative of the expression. We're well familiar with the u prime idea at the ends of these kinds of derivatives, but the idea is that the derivative of hyperbolic sine is hyperbolic cosine fundamentally. The derivative of hyperbolic cosine is hyperbolic sine fundamentally. So it's a very easy transition between these two. It gets a little more complicated from there, but there are similarities with our trig functions that we can probably see through here. Now just use these as forms that we want to meet when we are faced with problems involving derivative. It's pointless, I think, to try to memorize these and then use them from memory. Just kind of keep the list handy, or find the page in your textbook where you can look it up. So if you were faced with a problem like this, the derivative of hyperbolic sine of this expression, you would look over at the form and you would see in the form that the derivative of hyperbolic sine is hyperbolic cosine times the u prime. Okay, let's meet that form, you see. So the hyperbolic cosine of the expression means the hyperbolic cosine of this expression times the derivative of the expression, which is 2x. And we'd probably write it as 2x times hyperbolic cosine of the expression. Well, we can involve, as you might imagine, our other rules for derivative, our other derivative kinds of functions. Let's take a look at a couple of other examples. Here's one involving the derivative of natural log of hyperbolic cosine of x. Well, we recall that the derivative of natural log of some expression u is u prime over u. But here the u prime is the hyperbolic cosine of x. And if u is the hyperbolic cosine of x, then u prime, you see, would be the derivative of this. Well, that's simply hyperbolic sine of x. And since we're talking about x and not an expression, you see, then the derivative of x is simply 1, so we have hyperbolic sine of x. Okay, so then the u prime over u is simply this over the u, which is hyperbolic cosine. Oh, hyperbolic sine over hyperbolic cosine, that's hyperbolic tangent of x, you see, as the result of this. So we simply involve some of our old procedures with the new ideas that we have here. Here we have one involving the product rule and some other ideas. We have the derivative of the two terms here, so we separate our thinking into the derivative of one term minus the derivative of the other term. Here we're using the product rule. So we have, let's see, it'll be x times the derivative of sine, of hyperbolic sine. The derivative of hyperbolic sine, though, is hyperbolic cosine. So we have this, and then we have the hyperbolic sine times the derivative of x, which is simply 1. And then over here we have the derivative of hyperbolic cosine, which is hyperbolic sine. Then collecting here, plus this minus the same thing that goes out, so we simply have x times hyperbolic cosine of x. By the way, students tend to have some rather creative ways of describing or saying the hyperbolic functions. You can come up with your own versions if you'd like, but I've heard students refer to this as cosh. You see, just kind of making a little word out of this instead of always having to say hyperbolic cosine, cosh. and for sine, hyperbolic sine, sinh, or something like that. Just some kind of word that easily allows us to be referring to a hyperbolic kind of function. All right, consider this problem. Find the relative extrema of f of x is this function. We would follow through with the procedures that we learned before about finding relative extrema. And that means that we'll find the zeros of the first derivative function. Let's find the first derivative. F prime of x means, well, let's see, the derivative of this. We're thinking about the derivative of that minus the derivative of this. And here we're talking about the product rule. So we have, let's see, x minus 1 times the derivative of this would be hyperbolic sine for this factor. And then we would have this times the derivative of that. So it's hyperbolic cosine times the derivative of this, which would simply be 1. And then the derivative of hyperbolic sine is hyperbolic cosine. These terms go out, so we have simply this, and now we want the zeros involved in this first derivative function. And the zeros will be our candidates for extrema. Now, let's see, we find the zeros like this. We're looking for the zeros of each factor. The zero involved here, the value of x that will cause this factor to be 0 is simply x equals 1. Now the value of x that will cause this factor to be 0 is a little bit more elusive. We might say, all right, let's set hyperbolic sine of x equal to 0 and evaluate. Well, where do we go from there? We have no experience with this. You know, if we're talking about trig functions, we can often just think about how the graph goes and be able to decide on values at certain positions. Well, with hyperbolic sine, hyperbolic cosine, we don't have the value of that experience. However, we can do this. We can look at the graph in the textbook and decide that we have a 0 at 0. That is, f of 0 is 0 in the hyperbolic sine world. Or we can take an algebraic approach. We can say, well, if I think about hyperbolic sine equals 0, then the definition for hyperbolic sine would be this. You see, set it equal to 0, and now solve this. You see, we're finding the value of x that makes this true. And so multiplying on both sides by 2 and then separating the two terms will allow us to think of e to the negative x on the right as 1 over e to the x power. Now cross multiply, we have, let's see, e to the x times e to the x is e to the 2x, and 1 times 1 is 1 on the right side. Now we're still trying to solve here, and we could jump into the calculator if we want to, perhaps here, or I think it's a little easier to just try to make the bases look alike in order to get into the exponential world. And to do that, let's see, we think of 1 as e to the 0 power, and with like bases, we can set 2x equal to 0 and find that x is 0. Okay, so x equals 0 and x equals 1. Those are the zeros of our first derivative function, and therefore they are critical values, values to be evaluated to find out what kind of extrema we're talking about, if we're talking about an extrema at all here, for those two values. And we would go through the second derivative test to be able to tell us. All right, so we could do that. Now, the points that we're talking about are points that we can identify like this. X equals 1 is 1 point, but what is f of 1? So it's 1, and then what's the y value? What's the f of 1 value? Well, the f of 1 we find by replacing x with 1 up here. Now, let's see. 1 minus 1 is 0. 0 times this, that term goes out. So then we have a 1 in place of this x, so we have negative hyperbolic sine of 1. So the point 1 and negative hyperbolic sine of 1 is one of the points that we're targeting. Now the other point we're targeting has an x value of 0. But now we have to find f of 0. Well, I'm showing here that it's negative 1, but why is that? Well, let's jump back up here and see. F of 0. If this is 0, we have negative 1 times, let's see, hyperbolic cosine of 0. What does that mean? I don't know. We'll test it in just a moment. Let's see, when x is 0, we have, let's see, hyperbolic sine of 0 is 0. We found that earlier. Now, what about hyperbolic cosine of 0, though? We have the negative of that we're trying to evaluate here. Well, if you get into a jam like that, algebraically, you can get yourself out of the jam by going to the definition of the hyperbolic function that we're talking about. So here we're trying to evaluate the negative of hyperbolic cosine of 0. What does that mean? Well, we know that hyperbolic cosine is, if we were talking about hyperbolic cosine of x, then it would be e to the x plus e to the negative x over 2. And since we're talking about 0 here for x, it's negative e to the 0 plus e to the negative 0 over 2. But e to the 0 is 1, and e to the negative 0 is e to the 0. Well, that's also 1. 1 plus 1, that's 2. Oh, this becomes negative 1. You see, and that's why f of 0 is negative 1. If you get into a jam, though, go back to the definition, and it'll get you out of the jam. So the point 0, negative 1 is also one of the extrema that we're talking about here. We'll find out that this point is a relative minimum, and this point is a relative maximum. You know, I may have that backwards. I forget. You know, in going through this, I forget which is which here. The graph is in your textbook, and actually you should generate the graph for yourself. Your calculator may have hyperbolic functions as a possibility on it, but if it doesn't have that possibility, then certainly you could go to the definition again of those hyperbolic functions and put this in. You see, instead of hyperbolic cosine x, put in the definition of this in terms of e. And over here for hyperbolic sine, put in the definition in terms of e. You see that fraction in terms of e. And certainly then you can enter this into the calculator and find out whether these are relative maximum or minimum points. Consider this problem. It says power cables are suspended between two towers. Here are the towers, here's our cable, forming a catenary whose equation is y equals this. All right, so here's the equation corresponding to that curve. Now, we want to find the slope of the catenary at the point where the cable meets the right-hand tower. So we want to find the slope of the catenary at that point. Now notice the labeling here. A is the height of the cable at the midpoint here at its lowest point. And B is the distance to our secured point here at this tower, and negative B for the point at this tower. All right, so what we aim to do here, as we have so many times in the past, is find the slope of the tangent line at a particular point. All right, so what we're going to do is find the derivative here of y, and then find y prime at the point B. So we'll go over here to the side. Here's y equals a times the hyperbolic cosine of x over a. And then y prime, you see the derivative here is a times sine of this expression times the derivative of the expression, which is 1 over a. Now the a's cancel, so we have hyperbolic sine of x over a. Now we're ready to pop in that point. So the slope then at the particular point is y prime at x being equal to b. So we just pop a b in place of x, and we have the slope is hyperbolic sine of b over a. Now, we've seen this kind of thing before, and the emphasis here is that everything we've done before, we're doing now using hyperbolic functions and their related functions. That is, we're going to jump into inverse hyperbolic functions here in just a second. In fact, I invite you to look at those in your textbook right now. It isn't important terribly that we look at the list and see how the algebra is within all of them. It's just important that we be able to use them. So simply use the list as a reference to work problems. Here's a problem involving an inverse hyperbolic function. Now, let's lay out the problem first like this. Suppose we have a dock here and a boat, and we have a rope attached to the bow of the boat, and the rope is 20 feet long. Now, suppose a person that is standing right here at the edge of the dock holds the rope and walks along the dock. You see, then naturally the boat will be pulled along some kind of path, and it turns out that this is the path that the boat will take. And so as the person walks along the dock, the rope will be pulled, you see, and here's the path of the boat. This path is called a tractrix. It's also a pursuit curve, but this tractrix, you see, in this situation, has a particular equation associated with it, and we'll look at it in just a second. Here's what we're going to do. We're going to calculate the distance required for the person walking the dock to travel so that the boat comes within a certain distance of the dock. You see, somewhere along this path, the boat is a particular distance from the dock, and we're going to want to calculate this distance. Now, I want you to notice that this distance is really that distance plus this distance. And this distance, it turns out, is pretty easy to calculate. Let's read the problem, and we'll come back to the figure in just a second. Here's the equation for the tractrix. It is y equals, now notice the inverse hyperbolic secant here of x over a. A is the coefficient here. Now, this a value is the length of the rope, and then minus this amount. All right, a is the length of the rope. If a is 20, find the distance the person must walk to bring the boat 5 feet from the dock. Now, it's that distance that the person is walking. Let's come back over here and revisit the problem. This point is the point to which the person needs to walk in order for the boat to come as close as we want it to the dock, 5 feet in this case. Now, the y1 is this vertical distance, and that's what we're trying to calculate. How far is this person having to walk? All right, now, notice that the y associated with that equation is the y, the vertical distance associated with points on this graph. So those vertical distances are what we're talking about for y in the equation involving the inverse hyperbolic secant. All right, now if this is the point xy, this is the distance y that we're talking about and can be calculated from that equation. Now, if we take that distance y, and that's this distance y, and then add this distance, we'll have the total distance y sub 1, y subscript 1. Now, this distance can rather easily be calculated. I'll calculate it as a variable here. Let's just call this x. We have an xy here. That's the y. Here's the x. Okay. Now, this is just a right triangle. The length of the rope is 20 feet. I've reproduced this right triangle down here. So the rope is 20 feet. The distance here is x. So using the Pythagorean relationship, we'll find out that this is the square root of 20 squared minus x squared. All right. So that's this distance. Now, so that's what this is. So, in calculating this y1, it is, let's come back over here, it's the y1 is y, the vertical distance associated with that equation up here, plus that square root of 20 squared minus x squared that we just calculated. Now, let's put in the information about y. All right, now that information is from right up here. I'm just going to pop that down here. All right, so this y is this, and this I bring down right here. All right, now, this is minus radical plus same radical. They go out, so we have simply this. So y1 is 20 secant, or excuse me, 20 times the inverse hyperbolic secant of x over 20. And the x we want to be 5. For an x of 5, we can make the calculation here. Let's come up here. We have, for an x of 5, the x that was here becomes a 5. And now we make the calculation. And here's where we have to look at or reference our inverse hyperbolic functions. And so for inverse hyperbolic secant, we know that's ln 1 plus the square root of 1 minus x squared over x. Now the x here is this fraction. It's 5 over 20, which becomes 1/4. So it's 1/4 squared and 1/4 in the denominator. And all we need to do is clean this up a little bit. So we have 20 times. Now I've multiplied 4 times the 1 and 4 here because of the 1/4 in the denominator. So we have 4 plus 4 radical, and then 1 minus 1/16 turns out to be this. Now it's a calculator push, and we find y1 to be 41.27 feet approximately. So the person has to walk this far along the dock in order to bring the boat to 5 feet within the 5 feet from the dock. Well, we've talked about a lot of aspects of hyperbolic functions, and we've just touched on them a little bit. And there's one area we haven't even touched on. We have arrived at the point of talking about inverse hyperbolic functions, and we can look at the list in the textbook. We haven't even looked at the derivatives and integrals of the inverse hyperbolic functions. But again, I invite you to look at that list, and some problems on your homework may arise from that list. And just reference them. Just go back to them and attack the problems just as we have so many times in the past using the trigonometric functions. Good luck.